All members of group 14, carbon, silicon, germanium, tin, and lead, exhibits an oxidation state of +4. But the +2 oxidation state increases in stability as the group is descended. Carbon and silicon are abundant on Earth. From group 14 elements, there are generally 4 valence electrons for each element. The covalent radius increases with the atomic number, so do the ionic radii if available. The electron activity value of carbon is the highest. Others have similar electron negativities. Group 14 elements can form covalent bonding, say single bond, double bond, even triple bond, or mixed bonding with many elements. There is a large difference between IE2 and IE3. The atomization energy decreases down the group, and the variation of the atomization energy leads to the variation of the melting point and the boiling point. Allotropies of carbon are widely investigated for diamond, graphite, fullerene, graphene, and others. Diamond is not the thermodynamically most stable form of the element, but is metastable. Graphite is more reactive than diamond, reacts with oxygen at higher than 970 K, while diamond at higher than 1170 K. Graphite has a layered structure. See the structure here for reference. Then it can form intercalation compounds. There are 2 general types of graphite intercalation compound: intercalation with associated reduction of the graphite by metals, and the intercalation with oxidation of graphite by an oxidizing agent such as bromine, nitric acid, or sulfuric acid. Question: what is the working mechanism of a lithium-ion battery in your mobile phone or other electronic devices? Usually, carbon with a layered structure is employed as one electrode. Carbon is intercalated with a lithium ion, while lithium cobalt oxide, another electrode, loses its lithium ion during the charging and the battery. In discharging process, the carbon deintercalates, lithium ion goes back into cobalt oxide and recover to lithium cobalt oxide again. The chemical equation is shown on the right. Fullerenes are reactive. For example, react with oxygen to form fullerene oxide, forms the derivatives with various structures through addition reaction, even forms charge transfer complexes with some organic molecules. C60 can be oxidized to lose 3 electrons, also can be reduced to receive as many as 6 electrons through 6-step sequent processes. Such a redox behavior had been predicted theoretically and later proved experimentally, though very difficult. Carbon nanotube can be viewed as rolled up graphene. The 3 different chemical structures shown here results in different semiconducting properties. Chemically derived carbon nanotubes have many applications in device fabrication. Higher purity of silicon means higher efficiency of the corresponding devices. There are 2 main methods to purify silicon chemically. See the slide. Trichlorosilane is the key intermediate in both methods. Here are some typical chemistry of silicon, germanium, and tin. Silicon germanium reacts with oxygen, fluorine, chlorine, and others at high temperature to give binary compounds. Silicon reacts with aqueous alkali to generate hydrogen. Silicon is soluble in the mixture of concentrate nitric acid and hydrofluoric acid. Germanium reacts with concentrated nitric acid, hydrogen sulfide. Tin reacts with diluted nitric acid, concentrated hypochloric acid, or concentrated sulfuric acid. Tin reacts with hot aqueous alkali. Saline is a colorless flammable gas, reacts with oxygen, base, and active metal. For example, potassium. Germane, a colorless flammable gas, also reactive to potassium. The carbon tetrahalides differ markedly from those of the later group 14 elements. They are inert towards water and dilute alkali, and do not form complex with metal halides. In fact, carbon tetrafluorides and carbon tetrachloride are thermodynamically unstable with respect to hydrolysis, but kinetically stable. Be cautious. Carbon tetrachloride reacts with a strong base, for example, sodium, violently. Silicon tetrafluorides and silicon tetrachloride are molecules with tetrahedral structure, react readily with water. See the equation on the slide here. You may ask, why does silicon tetrachloride react with water, but carbon tetrachloride not? It's believed that the size of the carbon in carbon tetrachloride is too small to be fully covered by the 4 chlorine atoms, away from the attack of water. The size, if silicon in silicon tetrachloride is big, the chlorine atoms cannot shield the water effectively. The germanium X4 family are more stable than GeX2, while PbX2 halides are more stable than PbX4. This is explained by the thermodynamic 6s inert pair effect. The preference for the +2 over the +4 oxidation state increases down the group 14 is the result of thermodynamic 6s inert pair effect. Tetrachlorides of germanium hydrolyze like silicon tetrachloride. The typical oxides of group 14 elements include CO, CO2, and others. The bond in CO is the strongest known in the molecule. CO2 is quite inert, unlikely to react. Silica, the only oxide of silicon, expressed with the empirical formula SiO2. Tin dioxide is soluble in many acids, but exhibits amphoteric behavior. Tin dioxide and lead dioxide are thermally unstable. Only lead forms a mixed oxidation state oxide, Pb3O4, named red lead. Group 14 elements can form disulfide and monosulfides, for example, CS2, usually used as a solvent in organic chemistry.